Welcome back, AP Statistics. This is part 2 of chapter 17. And I think it'll be helpful to start with a little bit of review about what we did last time. The sampling distribution model for a sample proportion is what we were talking about last time. Basically, a sample proportion can be understood as a random variable in its own right. And as a random variable, it fits a particular model. Provided that the sampled values are independent and the sample size is large, we talked about what that meant last time, the sampling distribution of p hat, that is the sample proportion, can be reasonably modeled, not perfectly, but reasonably enough, by a normal model where the mean of that normal model is going to be the assumed population proportion, which we call p without a hat, and the standard deviation would be this, square root of the quotient of PQ over N. So let's do some practice with some just comprehension questions. You want to poll a random sample of 100 students at a large university to see if they are in favor of the proposed location for the new student center. Of course, you'll get just one number, your sample proportion, p hat. But if you imagined all the possible samples of 100 students you could draw, and imagined the histogram of all the sample proportions from these samples, not only would you have an impressive imagination, but you would also be able to answer this question. What shape would it have? Well, the shape it would have would be unimodal and symmetric. Going back to the last slide, this normal model right here is what we would see, centered at the population proportion that is assumed, and the standard deviation being square root of PQ over N. So it'd be unimodal and symmetric. Where would the center of the histogram be? Well, as we saw, it's at the assumed population proportion. Now, number 3, I want you to think about a little bit. If you think that about half the students are in favor of the plan, what would the standard deviation of the sample proportions be? Take a moment, think about this, pause the video, and unpause when you think you have an answer to this question. All right, let's see what it is. The standard deviation is the assumed population proportion P times Q, the complement of that, all divided by N, our sample size, and that's all under the square root, right? So we have the square root of PQ over N. Now, how do we get P and Q? Well, we think that about half the students are in favor, which means half the students would be not in favor or have no opinion whatsoever. So we'd have half in favor times half not in favor, dividing all that by 100 and then square rooting it, we would get a standard deviation of 0.05, 5%. So now we're going to switch gears and we're going to talk about the sampling distribution, not of the sample proportion, but of the mean. All right, this is going to be a bit different, but there is a remarkable similarity. We're going to see a bunch of histograms, and these are the results of rolling n fair 6-sided dice and finding the average roll. And we're going to repeat it 10,000 times. So we have 10,000 trials of this simulation rolling some number of fair 6-sided dice. And we would, of course, use a computer program to simulate the die rolls, which is what our textbook did. I'll be showing you an image straight out of the book. Note that as the number of dice n increases, the distribution follows Demoire's conclusion, though a die roll does not constitute a Bernoulli trial. For a fair 6-sided die, there are, of course, 6 outcomes, and 6 is more than 2. So watch this. This is 10,000 simulations of rolling one die. That is clearly a uniform distribution. What if we toss 2 dice, and we would then find the mean of those 2 dice? Well, this is what we would get. And that is definitely not uniform. although it's more upside-down V-shaped than bell-shaped. But once I start throwing 3 dice, we start seeing a bell-shaped trend happening. Now, what if I threw 5 dice? Oh, that is definitely bell-shaped. And if I haven't convinced you yet that something is going on, I throw 20 dice and find the average 10,000 times. That's a bell curve right there. That is a unimodal and symmetric curve, no doubt about it. But again, we're not talking about a sample proportion. We're talking about a mean die roll. This is no longer a proportion, so we need a new theorem. That theorem is one of the most important theorems in all of statistics, and you can make an argument that this is the most important theorem in all statistics. This is the central limit theorem, or CLT, proven rigorously by Pierre-Simon Laplace, who you see to your right. The sampling distribution of any sample mean becomes more nearly normal as sample size increases and observations are independent and observations are collected with randomization. All right, so independence, randomization, those words you see all the time. And what's amazing is this is true regardless of the distribution of the population. The more skewed the population, the higher the sample size you'll need to get that nice bell curve. But what this is saying is that the sample mean, like the sample proportion, is a variable that, assuming a large sample size and a couple other things, fits a bell curve. And it doesn't matter how the variable that you may be analyzing is distributed. The mean of that variable is a normally distributed variable. All right. Now, what I said there might go over your heads a little bit the first time. Maybe you got it, maybe you don't. Once we get to some examples, you'll see what I mean. So this is the central limit theorem. The mean of a random sample, all right, so a sample mean is a random variable in its own right, whose sampling distribution can be approximated by a normal model. Not perfectly, but approximated. The larger the sample, the better the approximation will be. And what's amazing is there is, for any possible variable you can imagine, there's a sample size you can pick that's big enough that that sample mean will be a random variable that is distributed according to a normal model. It doesn't matter what you're studying. If you're finding a mean of a large sample, regardless of whether the variable itself is left skew, right skew, bell-shaped, U-shaped, whatever shape you think you want to work with, the mean of a large sample from that population is a normally distributed variable. And that is amazing. So here is how the central limit theorem works. So we start with any population, right? So the population we're looking at here would have a histogram that is very, 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 very right skew, okay? So this is not a normally distributed variable. Suppose we took many samples of size n from the population, and we'll assume that n is a large number, okay? Now, how large? We'll get to that. So suppose we took many samples of size n from the population, all right? Now, all of these samples right here are not bell-shaped. They resemble the population. If you take a sample from a large population and you sample well, your sample's distribution is going to represent the population's distribution. It's a representative sample. We're not talking about the population's distribution. We're talking about the distribution of means of large samples drawn from the population. So from our first sample here, we can find a mean. From our second sample, we can find a mean. From the third sample, we can find a mean. From any sample we can find a mean. And then we see how those means stack up, okay? So the histogram of the means of all those samples is unimodal and symmetric regardless of the population, regardless of the random variable itself that we are studying. The sample mean for a large sample is itself a random variable that will, given a large enough sample size, always fit a bell curve. Amazing. The sampling distribution of sample means can be described with a normal model. That normal model is centered at the true population mean, and that's the mean of the population up here, and has a standard deviation of the population up here divided by the square root of n. All right, so the random variable that is the sample mean has the same mean as the population, but a different standard deviation, and notably, a smaller standard deviation. So the normal model does not always describe the sampling distribution of sample means. We need to make sure that we have fit a couple of conditions, a couple of criteria before we assume a sample mean fits a normal model. All right, once we check off these boxes, we can assume that the sample mean will fit a normal model. The central limit theorem holds given the following assumptions. The independence assumption, all right? Independence, one of the biggest terms in statistics. Keeps applying, you'll see it all the time through the rest of the year. The individuals in the sample must be independent of each other. To assume data are independent, or essentially independent, we can check two familiar conditions. You got randomization condition. For experiments, subjects should be randomly assigned to treatments. For surveys, the sample should be a simple random sample or something of almost equal merit, like for example, a systematic sample, cluster sampling, stratified sampling, not convenience sampling, or something silly like that. And the 10% condition. Less than 10% of the population has been sampled. If any beyond that, and you cannot assume independence anymore. Also, we need to check the large enough sample condition. The sample size n must be large enough. Now, how large is large enough? Short answer. If n is greater than or equal to 30, sample size of 30 or greater, the sample size is generally considered large enough. 30 is kind of like the magic number for this case. Sample size of 30 or larger, and the sample mean will assume a normal distribution. The sampling distribution of sample means will assume a normal distribution. All right, well, what's the long answer? Well, the long answer is it depends on the distribution of the population. The more skewed the population, the larger the sample required. So a sampling distribution of sample means for a really, really skewed population, you're going to need a really big sample size. You're going to need a sample size bigger than 30, but we'll cross that bridge when we get to that. So, in general, if the sample size is greater than or equal to 30, regardless of the distribution of the population, and the sample size is less than 30, or should I say, or the sample size is less than 30, but the population is at least approximately normally distributed. So if we have a sample size less than 30, but the population fits a bell curve, the sampling distribution of sample means will fit a bell curve as well. Central limit theorem may be used. We will tackle obscure cases with really skewed populations later on in the lesson. So, we're going to now compare the sampling distribution for the sample mean with the other sampling distribution that we talked about, namely for the sample proportion. Assuming all appropriate conditions are met, recall that the sampling distribution for sample proportion, that's p hat, follows a normal model where the center of the bell curve is at the assumed population proportion, and the standard deviation would be that radical Velleman. The sampling distribution for a sample mean, namely x bar, or choose your variable bar, follows a normal model where the mean of that bell curve is the assumed population mean. Standard deviation is the same as the standard deviation of the population, but divided by the square root of the sample size. So again, similar to the population of the random variable itself, but notably a bit smaller because of that square root of n in the denominator, making the proportion smaller. Let's do an example just so you know how to apply the central limit theorem, okay? And by the way, when I say central limit theorem, or CLT, that is the theorem that proves the sampling distribution model for the sample mean fits a bell curve centered at the population mean and with a standard deviation of the population standard deviation divided by the square root of n. That's what central limit theorem says. So, a college phys ed department asked a random sample of 200 female students to self-report their heights and weights. But the percentage of students with BMI over 25 seems suspiciously low, as we found in the last video. One possible explanation may be that the respondents shaded, quote unquote, their weights down a bit. The CDC reports that the mean weight of 18-year-old women is 143.74 with a standard deviation of 51.54, but these 200 randomly selected women reported a mean weight of only 140. Based on the central limit theorem, does the mean weight in this sample seem exceptionally low, or might this just be random sample-to-sample variation? So, we need to check to make sure our conditions hold, and it looks like they do. Let's look at the large enough sample condition. Distribution of college women's weights is likely to be unimodal and reasonably symmetric. CLT would work even for small samples. 200 values is way more than plenty. Honestly, you could get away with less than 30 here, so 200, that's awesome. Randomization. The women were randomly sampled, and their weights can be assumed to be independent. And 10% condition, fewer than 10% of all women at the college were sampled. That is also a safe assumption. So, now what do we have to do? We're able to use a normal model by the central limit theorem. So, here we go. We are going to use normal CDF and analyze a bell curve to see what are the odds that given a mean of 143.74 and a standard deviation of the population standard deviation divided by the square root of the sample size, that our weight is 140 or less. That is the mean weight. So here we are at the calculator. I've entered all the relevant information in. We're going to hit paste and see what we get. It's a reasonably likely event. So how do we answer our question? There's about a 15% chance that the mean weight is 140 pounds or lower. That's what normal CDF told us. That's what analyzing our bell curve told us. The discrepancy between our sample and the CDC's report may be due to sample-to-sample variability. If we had, for example, say a 1% chance that the mean weight is 140 pounds or lower, okay, maybe there's some shady business going on. But the sample-to-sample variability may account for this discrepancy here. No reason to think with a probability as high as 15% that we can assume that people were being dishonest.